right, thanks for watching. And today, by popular demand, I would like to give you a glimpse into the exciting world of the calculus of variations. Now, the calculus of variations, it's a very exciting subfield of math which connects minimizers of energy with solution of PDEs. So you should think of calculus of variations just as being the bridge which connects the two. Now, I've already done a video on the calculus of variations, which are with a very basic example, but today I would like to focus more on the PDE aspects of it, and in particular, talk about one thing that's called Dirichlet's principle. So here is a setting. Suppose you have a domain, let's call it omega, and you're considering the following energy on omega. Let's call it I of u, where u is a function on that domain, and what I spits out, it's called the energy functional. It's simply the integral over that domain of 1/2 times the length of the derivative squared, 1/2 du squared, minus fu. So it's just a fixed function f times your function u. So this is the functional we'll consider for today. And if you've taken physics, you might recognize this actually as something very interesting, because 1/2 du squared, that's nothing other than the kinetic energy. So this is the kinetic energy, and this is the potential energy of your system. And what I of u gives you is the total energy of your system. So in calculus of variations, as I said, you connect energies with PDEs. And so this is our energy, and later we would like to ask, what is the corresponding PDE? And that said, though, notice in this functional, we can't just plug in a random function u. For instance, if you put an absolute value, this doesn't work. So we need to talk about a very specific class of functions called the admissible class. So MathCal A, and what it is just a set of all functions v, which in this case, let's say they're infinitely differentiable. And not only that, let's add a boundary condition. Let's require that our function u equals to some fixed function g. So in other words, the function we're considering are all the smooth functions that are equal to g on the boundary. And now we're ready for the minimization problem, which is the following. Namely, among all the functions v that in this admissible class, so that are infinitely differentiable with this boundary condition, find the one or the ones that minimizes energy I of u. So more compactly, what the minimization problem is just written as the minimum of v in that admissible class of I of v. So again, as I said, among all the functions v, try to find, again, if it exists, the function u which minimizes this energy. And here's a cool thing. So again, we're done now with the energy aspect of calculus of variations. But remember, calculus of variations, it not only has to do with the energy, but with the PDE. So without further ado, I can now state the main result of today, which is called Dirichlet's principle. Namely, if a function u solves this minimization problem, so suppose u minimizes the energy, so min v in a of I of v, then it turns out it solves a very specific PDE, which in this case, it's Poisson's equation. So minus Laplacian of u equals f in our domain, and u equals to g on the boundary. And this is sometimes called the Euler-Lagrange equation of this minimization problem. So maybe in another video, I will show that given a minimization problem, you can extract a PDE from this. But wait, there's more. This is always true, but it turns out in this specific case, the converse is true as well. Namely, U solves this minimization problem if and only if it solves the Poisson's equation. And this is what we want to show today. And in fact, as they say, the proof is in the pudding. So today's pudding is very delicious. And this is why I wanted to make the video. So let me prove this. So let's do the first part. And the first part is very standard. So, and it's nearly the same proof as the derivation of the Euler-Lagrange equations. And it goes as follows. So remember our minimization. So suppose U minimizes, let's say I of U, which is the integral over our domain of 1/2 du squared minus fu. I'm not cursing. It's just f times u. All right, so here's the important thing to understand. This is functional, depends on functions. It's very complicated. The beauty of calculus of variations is that we will turn this complicated problem into a single variable calculus problem. So even a Calc 1 student would be able to solve this. How? What I write down now, it won't quite make sense, but you'll see in a second why it makes sense. So let V be in C infinity of omega with V. So with a V identically equal to 0 on the boundary be fixed. So we consider an arbitrary function V that is 0 on the boundary. So in terms of a profile picture, so if this is omega and this is the boundary, what V looks like is just 0 here, and then it's whatever in the middle, but 0 on the boundary. So again, kind of like fixing a wave string at 0. And then consider the following. So again, U minimizes are functional, V is arbitrary. And what we would like to consider is the following. So I, U plus tau V, which is just the following integral over omega of 1/2 d, I think U plus tau dV squared, and then minus F times U plus tau V dx. Literally replacing U by U plus tau V, and tau, it's not 2 pi, it's just an arbitrary real number. Now again, I want to emphasize, we know what U is. It's this minimizer. V is an arbitrary function. So UV, F is fixed. So really notice, this whole thing, all it is just a function of this variable tau. So it's actually a real function, like in calculus. And we call this little I of tau. And before I move on, remember there was this admissible class. So we said U was in the admissible class. So U was infinitely differentiable, and U is identically equal to G on the boundary. And V was defined as just being at 0 on the boundary. Well, notice, for every tau, U plus tau V on the boundary, that's identically equal to G plus tau 0, which is just Z on the boundary. So in fact, our U plus tau V, they're in our admissible class. They're in the correct class. Now, let's look at this function little I a little bit more. Okay? And remember, what we said was this functional had a minimum at u. So I of u was the minimum, which means for any other function v, it's bigger. But now let's think of this in terms of tau, or like I of tau. Then if I give you a random tau, then this becomes just the functional of u plus tau v. Now, what is this value? Well, it is the same thing as I of u plus 0v. So it's just the value of the little I at 0. So in other words, if you want to draw the graph of little I, it just looks as follows. So this is tau. This at 0, it is I of 0. And in general for tau, it is I of tau. Now, I want to emphasize little I, that's a function of one variable. So what do you know from calculus about functions which have minima? Well, by the first derivative test or something, we know that the derivative of little I at 0 equals 0. And this is what allows us to go from minimizers of functionals to PDEs. Literally, this is the key to the calculus of variations. Well, now the question is, of course, this raises a question, what is I prime and what is I prime of 0? Well, remember I of tau, that was integral over omega 1/2 du plus tau dv squared minus f u plus tau v dx if you want. And well, to differentiate I, well, you just got to use the chain rule. So just as usual. So I prime of tau is integral over omega, and then let's see. So 1/2, use the chain rule. So 2 times du plus tau dv, and then you differentiate this with respect to tau, which again, this is constant, becomes 0, and you get dv, dvd. But here we have a vector, here we have a vector. So to make a scalar, you dot it. You can also do it by component, it's fine. And again, this is constant with respect to tau. So really, if you differentiate that, you get minus fv dx. And then what you're left with is simply the following. So I prime of tau, that is integral over omega, du plus tau dv dotted with dv minus fv dx. And now we want to use our magic equation, namely I prime of 0. On the one hand, it's 0. On the other hand, you can just let tau be equal to 0 here. And you get du plus 0 dv dotted with dv minus fv dx. Well, and this jumps out, and you get integral of du dotted with dv minus fv dx. All right, so what we know is this is 0 by assumption. Now, remember that v is arbitrary, and we kind of want to use this. So here we have this derivative. Ideally, we would like to put this derivative here, but of course we can simply by integrating by parts. Now, in integration by parts, they're usually boundary terms, but not here, because remember, v is 0 on the boundary. So yet another reason why we chose v to be 0 on the boundary, not only to have u plus tau v in the admissible class, but also for this integration by parts. So what happens here is that, well, this d comes here, and again, I've done a video on integration by parts, and you get minus Laplacian uv minus fv dx, which in the end becomes the following: integral of minus Laplacian of u minus f times v dx equals 0. Now, here's the thing. This function v is arbitrary. Arbitrary. So just to reiterate, what do we have? We have that for any function v, again, 0 on the boundary, if you integrate this function times v, you get 0. And the question is, what is this function? So again, suppose I tell you a mystery function such that no matter which function you multiply with and integrate, you get 0. Well, the mystery function has to be 0. So in other words, I'm using the following fact. If fg equals 0 for all g, then f must be identically equal 0. And if you want quick proof of this, suppose it's not 0 at a point, then it's, let's say without loss of generality, it's positive at the point. Then if f is continuous, then f is positive on some ball, and basically just choose v to be a positive function on that ball, but such that it's 0 on the boundary. You can do this. It's called a cutoff function, and therefore, in the end, you get that we get a contradiction. So f must be identically equal 0. So in particular, what do we get? We get that this inside function is identically equal 0. And what does that tell us? It tells us that minus Laplacian of u minus f equals 0. And therefore, in the end, we get Poisson's equation. And there was also a boundary condition, but remember, u was in the admissible class. So by assumption, u is just g on the boundary. All right, so that was the first part. Again, very classical. The derivation of the Euler-Lagrange equation goes the same. But let me also quickly prove the other part, since this is very fun, actually. So suppose now that u solves so minus Laplacian of u equals f, and then u equals g on the boundary, and let v in our admissible class, so v is smooth and equal to g on the boundary, be arbitrary. Or, yeah, let's say it's be arbitrary. And what we want to show essentially is that u minimizes the energy. So what we want to show is that I of u is less than or equal to I of v. So no matter which function we pick, u min is the energy at u is smaller than the energy of v. This means minimization. And here's a cool trick. Consider Poisson's equation. So minus Laplacian of u, let's say minus f. On the one hand, this equals 0. On the other hand, well, let's take this equation and multiply it by u minus v. Why are we doing that? Because u minus v is actually 0 on the boundary. So let's take that and integrate over our domain. Then on the one hand, what we get is that this thing equals 0. So integral of over omega, if you want, of minus Laplacian u times u minus v minus f times u minus v equals 0. And which, if you want, you can just write as integral over omega of minus Laplacian u minus v equals f times u minus v. But now, because, again, we want to turn this into derivatives, let's just integrate by parts. Again, there might be boundary terms, but not here, because remember, on the boundary, u minus v is just g minus g, and that's 0 on the boundary. So point is, for integrating by parts, you don't have to worry about boundary terms. And then what you get is basically du dotted with d u minus v equals, again, integral of fu minus fv. And this just becomes, if you expand it out, integral of du dotted with du minus du dotted with dv equals integral of fu minus fv. All right, good. So ideally what we would like to do, let's put all the u's on one side, all the v's on the other side. So we get integral of du squared, and then let's put fu here. So minus fu equals integral of du dotted with dv minus fv. Now this is good, except there are two issues. On the one hand, in our functional, there was this 1/2, so it almost looks like our functional. On the other hand, well, here we have u and v. Ideally, we just want to have v. And the way to solve this is with the following clever trick. So take this, du dotted with dv. Well, a function, a scalar function here, it's always less than or equal to its absolute value. Now, here we have absolute value of a dot product, which should remind you of the Cauchy-Schwarz inequality, or Cauchy-Schwarz-Bunyakovsky, which says that the magnitude of the dot product is less than or equal to the magnitude of those two vectors. So in particular, what we get, this is less than or equal to du times dv. Again, this means norm. And moreover, we have to use another equality called Cauchy's inequality, which simply says AB is less than or equal to 1/2 a squared plus 1/2 b squared, which you can simply prove because a minus b squared is greater or equal to 0. Expand that out and solve for AB, and you get this thing. So in this problem, what this becomes is integral of 1/2 du squared plus 1/2 dv squared. And it's good to isolate, like here, it's very good if you're dealing with products, because now instead of having du and dv entangled, you can just separate them out. All right, very good. And why is this useful? Let's come back to this thing here. So we had integral of du squared minus fu. I'll stop with the cursing in a second. And so we get du dotted with dv minus integral of fv. But now we found that this thing is less than or equal to 1/2. It is 1/2 du squared plus 1/2 dv squared minus fv. All right, and again, this is du squared minus fu. All right, and then we're almost done. So here's a cool thing. And again, it's almost magic. Those energy methods, it's always like magic here, because here we have du squared, here we have 1/2 du squared. If you put this here, I don't know why it's so thick, but you basically get 1 minus 1/2 of that, which is just 1/2 of this. So in the end, what you get is indeed, so integral of 1/2 du squared minus fu is less than or equal to integral of 1/2 dv squared minus fv. And in the end, we do get beautifully our inequality that IU is less than or equal to IV. So in fact, U minimizes our energy. So U minimizes I. So in the end, what we've shown is that U minimizes our energy if and only if it solves Poisson's equation, which gives a nice, energy interpretation to a Poisson's equation. Namely, the solutions, they minimize that total energy, if you like. And again, so I want to emphasize this direction is always true in calculus of variations. This one is very specific to this equation. That's why I wanted to cover this. And also the proof, I think, is just beautiful. All right, I hope you like this. If you want to see more math, please make sure to subscribe to my channel. Thank you very much.